So 4.3 is going to be on mean value theorem eventually, but we're going to start this video with something called Rolle's theorem, which is really a particular case of mean value theorem. So let's kind of walk ourselves through the conditions and kind of just graphically we'll be able to, I think, make a lot of sense of why this theorem makes a lot of sense. So it says let f of x, or let f be a function defined on a closed interval from a to b. So I'm just going to draw some nice kind of, maybe polynomial function, whatever it might be here. So this is going to be my f, and I need some interval in here from a to b. So let's say this is starting over here at a, and then let's just say this is, oops, hold on just a second. And then let's kind of read through our criteria here. So, because the dot I drew wasn't going to work for us. So it's continuous on the closed interval, differentiable on the open, which it needs to be because technically by definition you don't have continuity at a closed, or you don't have differentiability rather at a closed endpoint. And then the last part of the condition says that f of a needs to equal f of b. So suppose that's my a, and then this I needed to be my b, or I needed at least some location where the outputs of these two coordinates, f of a and f of b, are both equal and they're at this value right here. All right, so that's the other, kind of the third condition of our Rolle's theorem. All right, so as we look at this, I think we can, hopefully all agree as we look at this part of our function. So we are from a to b, we are definitely continuous and differentiable on the open interval. All right, so what's the conclusion? There has to be at least one number c in this interval where f prime of c is equal to 0. So f prime, of course, is the slope of our tangent line, so we're looking at locations where f prime would equal 0. So certainly this is a location where my f prime is equal to 0, and let's call this C1, because I happen to have drawn a picture here where there's actually a couple of locations, but there has to be at least one. And then over here, it looks like I have another location. If I think about my drawing in my tangent line here, this is another location where f prime of, and let's call this C2, so where f prime of C2 here is equal to 0. So the conclusion of the theorem is that these c values, at least one of these c numbers has to exist where the slope of the tangent line is equal to 0. So let's look at a couple of examples, determine if Rolle's theorem applies, and then if it does, approximate the values of c guaranteed by the theorem. Well, I'm very predictable. I didn't really look at my examples. I drew almost the exact same example, number one, that I did in my little motivation up above here. But let's just then quickly go through this one. So I definitely look to be, nice and continuous on the closed interval here and differentiable on the open interval. So things look good in terms of the first two conditions. And it also appears that the third condition, that f of a is equal to f of b. So let's kind of write out those. You will need to know these conditions, and you need to be able to write them out with the proper notation. So we are continuous on the closed interval, we are differentiable on the open interval, and the outputs, f of a and f of b, those y values are equal. So therefore, we know that our Rolle's theorem applies. And so the values of c that are guaranteed by the theorem, okay, so looking at places where we have a horizontal tangent line. So again, I apologize, I should have just taken a little peek down below and realized that I gave us an opening motivation of the theorem that was almost exactly like this first one. But these two values, so C1 and C2, these are the values that are guaranteed by the theorem. So C1 and C2, I'll just say, satisfy the theorem. All right, so let's look at another example over here. So as we look at this graph, I would say, kind of starting out, we definitely have, the first observation of the last condition looks to be met. Certainly looks like the f of A is equal to the f of B. So it certainly looks like, we are continuous on our closed interval from A to B. It looks like f of A is equal to f of B. Okay? But in this case, f is not differentiable on the open interval from A to B, and that is because we are not differentiable at, and I'll just say at this value, let's just call it, I don't know, k. We'll say at x equals k. So where we have this sharp turn in the graph, this corner point, if you will, we are not differentiable. So therefore, the Rolle's theorem does not apply. Okay, therefore, Rolle's theorem does not apply. And in fact, there is no place where f prime is equal to 0 between the interval on the interval from A to B. So in this situation, not only does it not apply, that doesn't necessarily mean there couldn't be a value where f prime is equal to 0, but actually in this case there is not. All right, so Rolle's theorem does not apply. All right, so let's look at a couple more examples here, and we're just going to look at these from a more algebraic standpoint, kind of looking at them computationally. So suppose I have f of x is equal to, and let's just say I have x to the fourth minus x squared on the closed interval from -1 to 1. So first of all, you need to be able to state your conditions. So certainly you have a nice polynomial function. So when you have a nice polynomial function, you're not going to have any issues of violations of continuity or the differentiability, but you do need to be able to state it. You don't have to go through and really prove it in any way. This one should be kind of obvious, but you definitely need to be able to state those. If you're not sure, I would say take a look at the graph and see if you see any issues with either continuity or differentiability, but this one should be obvious without having to do that. Now, the last condition then that we need is we have to check out what f of -1 and f of 1 are, and in this case they are both equal to each other. They happen to both equal 0 in this case. It doesn't matter what they equal, it just matters that they equal each other. Okay, so our three conditions for Rolle's theorem are met. So let's just say, so our oops, got a little sloppy there. So our Rolle's theorem applies. All right, so let's actually find the values of C guaranteed by the theorem. Okay, so we're looking for where f prime, so f prime in this case is just 4x cubed minus 2x, and we're looking for where f prime is equal to 0. So I think here of what we just factor out a 2x, and we'd have times the quantity of 2x squared minus 1 equals 0. Setting each of our factors equal to 0, we have our 2x equals 0 and our 2x squared minus 1 equals 0. And then just dividing by 2, and on the second equation adding our 1. So we're just going to have here that our x is equal to 0, and then we have 2x squared is equal to 1. So finishing out the second one, if we divide by 2, then of course we are down to the x squared equals 1/2, and then just make sure that if you take a square root to get rid of a square, you're introducing that plus or minus square root on the other side there. And so we're going to have that x is equal to plus or minus 1 over root 2, because square root of 1 is 1, or if you prefer plus or minus root 2 over 2. And so in this case, we want the values that are in the interval, and in this case, all three of them are. So the values of, I guess, C, this is the other thing that we could have said. I could have, instead of using X here, I could have used C's. But the values of C that are guaranteed by the theorem, I'm just going to write them in a little set builder notation here. We'd have our negative square root of 2 over 2. We would have our 0, and then we would have positive square root of 2 over 2. So in this case, three values of C that are guaranteed by the theorem where f prime is equal to 0. But make sure as you're looking at your homework that you do check these three conditions. There will be probably homework problems where maybe one of the conditions fails, so make sure you're going through those conditions on the theorem there. All right, let's look at another example. So this one says find the two zeros of, let's see here, what do we have? F of x is equal to 3x squared minus 10x plus 3, and then show that f prime has to equal 0 at some point in between those zeros. All right, well, finding the zeros, or the x-intercepts, however you like to think about that, that just means you're subbing in 0 for y and solving for x. Now, if you're not so hot with your factoring, you may want to use quadratic formula here, but be able to solve this by hand. Some of you might like to go off to the side and do that AC method where you're looking for a 9 product, a negative 10 sum. That requires a few extra steps. But just with some trial and error, if we check this one out, it does factor to 3x minus 1 times x minus 3. And then, of course, you have your product equal to 0. So now just setting each of your factors equal to 0. So we have our 3x minus 1 equals 0, and our x minus 3 equals 0 here. So we're going to end up with one of our zeros is at x equals 3. And then, of course, the other one, when we divide by 3, is going to be at x equals 1/3. So here are our two zeros. So our two zeros are at 1/3 and at 3. All right, so that was the first part. Then it says to show, and so it doesn't say we actually have to find it, but it says to just show that f prime has to equal 0 at some point in between those two zeros. Okay, so let's just say, so because f of x is definitely going to be, it's a nice, again, polynomial, happens to be a quadratic or a parabola, because it is continuous on the closed interval from 1 to 3. And of course, it's also going to be differentiable on the open interval from 1/3 to 3. And we also know, of course, that f of 1/3 is going to equal f of 3. And of course, that's because in this case, they are both equal to 0. So because our three conditions are met, continuity on the closed interval, differentiability on the open, and f of the endpoints here are equal. So because of those things, what we know is that our Rolle's theorem is going to guarantee, so Rolle's theorem guarantees that there must be at least one point in this interval from 1/3 to 3 where f prime is equal to 0. That is Rolle's theorem. All right, so those are the kind of two steps of that. So I would call this, maybe we can refer to this as part B. So this is actually just, without actually finding that location where f prime is equal to 0, it's really just showing that that location must exist. So again, just kind of getting used to Rolle's theorem and the formality of writing out all the conditions of the theorem. All right, last one here for Rolle's theorem. So it says that we have the height of a ball thrown into the air from a window 32 feet above the ground is going to be given by, and it's our height function, let's call this h of t, is equal to negative 16t squared plus 16t, and then my t's and my pluses are starting to look alike here, plus 32. So negative 16 t squared plus 16t plus 32. Okay, so this is our height function. So first, verify that h of 0 equals h of 1. So if we notice here, sub in either 0 or 1, sub in both of them, and you're going to get 32 on both of those. And then I'm just going to kind of add to this. Once again, it's just a parabola, but let's just say and observe, left off my R there, observe that, observe that this h of t is definitely going to be continuous on the closed interval from 0 to 1 and differentiable on the open interval from 0 to 1. All right, so we have our three conditions that are met for mean value theorem. So now we can apply mean value theorem. So what is that? Application of mean value theorem says that there has to be at least one location where the h prime, which in this case would be our negative 32t plus 16, where h prime has to equal 0. Okay, so we're finding the values again of, and I could have used c here if I wanted to be strict in terms of always saying the values of c guaranteed by the theorem. But those are really just the input values. You call them x, call them in this case t. It's just the values guaranteed by the theorem. So let's go ahead and add the 32t to the other side, and then dividing both sides by 32, we get t is equal to 1/2. Now t is time, which I did not specify. The height of a ball thrown into the air is given by h of t. Let's go back to the original problem, and I'll just add this here and say where t is in seconds. All right, so we have a 1/2 second. So what happened at a 1/2 second? So we've applied Rolle's theorem. Now let's interpret it in this context. So what we have for our height function, hopefully we can, pretty easily think about what h of t looks like. It's going to be this parabola. At 0, it's at 32. And it has a negative leading coefficient, so of course it's going to open down. And so we're really only interested, honestly, in what's happening here in our first quadrant, because we're just talking about, this region, the height of the ball over t, as the input in seconds. All right, so we were finding that on our interval from 0 to 1, so from 0, and then this would have to be over here at 1. So on this interval where we were continuous on the closed, differentiable on the open, and both f of 0 and f of 1 were equal to 32, we just found that at 1/2 of a second, again, this is not necessarily drawn perfectly here, but at a 1/2 a second, we had our location where f prime, I guess this isn't really f, is it? Where h prime of a 1/2 is equal to 0. All right, so early observation then this is a really important application we're going to use a lot. Basically, when we reach that max height is when our derivative of the height function is equal to 0. So where that slope of the tangent line is equal to 0, this is going to be the interpretation. This is when the ball is at its maximum height. And we are going to use that fact a lot. When we come back next time, we're going to generalize this Rolle's theorem in a more general way, and then that's going to be mean value theorem. So we'll talk about that next time.